Got it. All right, so we are recording. I guess we'll get going. I'm going to talk a little about tools for debugging and profiling today. Um, there are a lot of tools for doing this. I'm going to try to cover a few of them and not in great depth because there are so many and we've only got about 40 minutes to talk about it. But I'm going to talk a little about debugging, a little about profiling, and the tools on the debugging side I'm going to cover printf, the compute sanitizer tool, the setting of environment variables, and then two actual debuggers, CUDA-GDB and DDT from ARM. And then on the profiling side, sort of the profiling counterparts of those tool chains, NVIDIA's Insight and MAP, also from ARM. So before we start talking about debugging, I want to just talk quickly about the types of bugs, because I think there's a lot of info that you can get just from the type of problem you're having that will guide how you approach debugging a problem. Does the bug you have cause your program to crash? That's really important. I think if you have a crashing bug, that's probably the best type of bug you can have because it's usually not subtle and it's usually somewhat easy to locate. Is it the type of bug that just causes your results to be incorrect? That can be a little more bothersome. And then particularly if you have a bug that does either crashing or sort of results in correctness, but it only does it intermittently, that points to some sort of maybe race condition that you have in your code. If you have a bug that kind of goes away when you try to examine it, you insert printfs and the bug sort of disappears. Sort of examining these behaviors that the bugs have can give you a little clue to what might be going on in your code before you even get a tool out of your bag to start examining what's happening. So just think about the bug that you're having before you start debugging. And, using a debugger, particularly in the context of debugging GPU code, I would say it's not yet as seamless as debugging on the CPU side is. So I think particularly for GPU debugging, it's nice to try a few simpler tools before you go to sort of the last resort step of really breaking out a debugger. So I'm going to start by talking about things you can do before you actually get a debugger out. So here, particularly using printf, you may have been derided in the past for using printf as your debugger, but I think it's a more reasonable thing to do on GPUs, at least at the moment. There are also some environment variables you can set to get additional information about your code, about variables and launching. And then there's this compute sanitizer tool from NVIDIA that can perform a lot of bug checking also, again, without the need to actually start a debugger. And the compute sanitizer tool can do things like look for out of bounds accesses. It can find some race conditions in shared memory. It can look for uninitialized access, and it can see if you're using synchronization primitives correctly. So briefly about printf, it's actually quite nice that the printf is able to print from debug code. My sort of primary GPU development days were in the early days of CUDA when you couldn't do this. And it was a huge bummer. So it's really nice when this was added, I think in CUDA 2 many years ago. But being able to simply print state and examine the state of the code from a CUDA thread on the device is quite handy. It can give you a ton of output if you just use it, sort of uncarefully. Because say you have a 1,000 thread blocks, each one has a 1,000 threads in it, then even there for a simple case, you're going to get 1,000,000 threads printing something to your screen. So you probably don't want to do a thing like that. If you have some idea of where a problem is occurring, it can be very helpful. So you can see in this little code snippet I have down there, I just have this if guard saying like, well, if I'm in block 99, have threads in the second half of the warp, have threads 16 through 31, print out the value of some variable. So if you have an idea of what part of the code might have a problem, if it's around the boundary of some data structure, and you can have only the threads that would be hitting that boundary of a data structure do some printing, then printf can be a pretty useful tool. For OpenACC in particular, there are a couple of environment variables that are helpful. And I'm mentioning this for OpenACC particularly because some of the debuggers seem to have a little bit more trouble debugging OpenACC code versus CUDA code. So there are these extra environment variables you can set. This ACC notify, NV ACC notify can be set to 1 to get some additional information on kernel launches, or 2 for data transfer information, or 3 will give you both. It produces a lot of output. Again, it's kind of a lot of stuff to go through, but it will tell you basically sort of what's being launched and when things are being launched. So if you have like a bug that crashes, you can sort of see where this output stops, and that might give you a good clue into what was happening right before the program crashed. Similarly, this NVACC debug equals 1, turning that on gives you additional information on, again, on launches and on the state of the device and what function arguments were being inserted into kernel calls. Similarly, it's a ton of output. So again, I don't know that you would want to actually print that out for a large code and go line by line through all of it. It's pretty overwhelming. So you kind of want to stock graph your way through it, or maybe just look at the tail end of it and see like where a program terminated and what were the lines around where a program terminated. That can give you some information about what kernel was being called and what arguments were going into the kernel. I'm going to talk about the compute sanitizer tool, but I want to just quickly introduce a really, really simple model bug that we'll use to explore some of its capabilities. So this one right here is just going to be an out of bounds access. You can see this tiny kernel basically will, it's got this obvious error where if assuming A, B, and C arrays are all the same size, for some reason we're writing to the index +1 element of the C array. So that will most likely be an out of bounds access. So if we've compiled our code very simply here with these arrays being 64 words in size, and then we're calling this kernel basically using 2 blocks with 32 threads in each block. So what we would expect to happen here in our model bug is that because of the way we're indexing inside this kernel, we'd expect the first element of C won't get written at all, and that the last write inside that kernel will occur outside the bounds of the C array. So if I initialize my variables, I initialized A array to the I +1 values and B to be the negative of that. Then when I add them together back in this kernel, I'd expect everything to be 0. I initialize C to -1, and then I run this code. And you can see we're getting what we would expect, right? The first element of C, I'm printing out C there, by the way. The first element of C doesn't get written to because we're indexing, and there's no crash or anything. So we suspect something got written out of bounds, but it didn't crash the program. So we can use the compute sanitizer tool to look at this code. Compute sanitizer has these 4 modes, like I mentioned earlier, and you can access them all by doing --tool and then the name. So here I'm using the mem checker. So running compute sanitizer tool equals mem check on this code, and indeed it verifies our assumption, right? So it catches this invalid global write of size 4 bytes. That was the single 32-bit int that we wrote off the end of that array. And then a little further down, it tells us what thread did it. So it was the last thread in the second block, which is what we would expect. And it tells us the line in the kernel where we should go look. So really, for a really simple bug like an out of bounds access, we know exactly where in our code to go make a fix without ever having to fire up a debugger. So that's certainly a great tool to use. And I think it's also worth mentioning here that this out of bounds access wasn't causing my code to crash. So just because you don't have a crash doesn't mean you shouldn't use these tools. It's a great idea to periodically run your code against some of these tools to see if it catches a bug before you become aware of it. I'm going to use another little model bug here to demonstrate the race condition detection. So this, again, this is a buggy kernel that has an unsafe increment of a variable that basically is taking a global variable, it's loading it into a shared local variable, it's incrementing that shared variable by 1, and then it's updating the global variable with it. Because all the threads are going to be doing this at once, you're going to get a lot of either, you're going to get all the flavors of race condition here, read after write, write after read, write after write. All these things will probably be happening in the code. So if we called this kernel on 1,000 blocks with 1,000 threads each, if there was no race condition, we would expect this value to get incremented 1,000,000 times. Since we suspect there will be a race condition, it will probably get a final value much less than 1,000,000. And here I'm running it a couple of times, and you can see its value is 16 one time and 12 the other time, meaning we definitely had some races going on. And you can tell that it's the answer is variable depending on, from one run to the next, you'll get a different answer. So classic sort of race condition symptoms. So the question is, can the compute sanitizer catch a thing like this? And indeed it can. So same invocation of the tool, except now instead of saying dash dash tool equals mem check, I'm saying tool equals race check, running it on this code. And again, it finds the data race immediately. So the first, again, this will produce like a ton of output. I'm just showing you the first thing it reports. But there were somewhere around 1 million problems that it found. And so it's, again, identifying the line. So looked in that kernel, it's saying somewhere around line 17, 18, you have some unsafe data access occurring. So that would be enough, again, to go in and look at the problem in our code without having to get a debugger out. But if you have a problem that can't be caught by one of these simpler methods, then there are a couple tools. CUDA-GDB is the one from NVIDIA, and ARMForge is the one. Forge is sort of the umbrella product that contains both DDT, which is the debugger, and MAP, which is the profiler. So DDT is the debugger from ARM. Both have the capability of debugging GPU and CPU code together. Neither one is perfect, but they definitely can provide some additional insight into your problem. And both of them seem to work a little bit better with CUDA than with OpenACC. And I think that's sort of just the nature of OpenACC being basically directives that are transforming your code. On the CUDA side, OpenACC will end up generating some CUDA kernels, but those aren't CUDA kernels that you wrote that exist in your code. So things get transformed, and it can be unclear, what the correspondence is between the state inside of the generated kernel and how it relates back to the OpenACC code you started with. So before you use a debugger, you need to make sure you're compiling with debug information on. So for CUDA codes, that looks like lowercase g that you're used to for getting symbol information on the CPU side, and the uppercase G does the same thing for a GPU. On the OpenACC side, again, the lowercase g is still necessary for the CPU debugging side. And then you adding this in this dash GPU statement, the CC70 you can ignore, but adding the debug and the no RDC flags are necessary. Debug, again, it will insert sort of the symbol information you need on the GPU, and the no RDC seems, that's telling it not to make relocatable device code, and that seems to improve the quality of some of the state information you can get inside a kernel. Another thing you can do is you can add this inside the dash GPU flag. You can add keep GPU, and then that will generate a file that has essentially the transformed OpenACC, the CUDA kernel that it's been created from your OpenACC code. That might be interesting to look through. I will say it is nothing like what you would have written yourself. They're pretty hard to read compared to the CUDA that you would write by hand. But you can still go through that and sort of understand what the compiler has done to your OpenACC code. Okay, so CUDA-GDB, I think probably the main advantage to CUDA-GDB is that it is just GDB. So if you're familiar with GDB, it'll be a very familiar tool. It's just been, all the CPU side stuff that GDB does, the CUDA-GDB still does all that stuff. So it just has extended with some additional capabilities so that it can work on NVIDIA GPUs, and it's got some specific extensions for CUDA code. It's very feature rich, but depending on the type of bug you have, not all of those features will be particularly relevant for you. Again, it works better for CUDA than for OpenACC, although it does, at least in certain cases, work pretty well for both. But it would be sort of my go-to if I had a CUDA problem, whereas if I had an OpenACC problem, I don't know that I'd start with CUDA-GDB. It works through the CLI or within an IDE. I think Daniel is going to talk about using it from within an IDE a little bit later, so I'm just going to focus on the CLI. One thing to note, it does use the /temp as a temp directory by default, but it does respect the temperature environment variable, so you might want to set that if you're doing an extended debugging session. And you can get full documentation. Probably the easiest thing is just to Google CUDA-GDB, but NVIDIA has a lot of documentation about it on their site. So I can't go, it would take hours to go through all the things that CUDA-GDB can do. So I'm just going to assume you are sort of familiar with GDB. If you're not generally familiar with GDB, I think it is a good tool for everyone doing development to be at least minimally aware of. It's a pretty useful little thing. But I'm only going to talk about sort of the CUDA extensions to it. And even that, like I can't go into depth on all the CUDA extensions, but if you're inside a CUDA GDB session, one thing you can do quickly to see what are the CUDA specific things it can do. You can type CUDA and then hit the tab, and tab completion will tell you that here are some commands. So CUDA block, CUDA device, CUDA grid, CUDA kernel, lane, SM thread, warp. Those are all things one can type. These are commands that basically help you either examine where your current focus is and also switch the focus. And by focus, I mean basically which thread inside of which block. And additionally, you can see the hardware side. So what SM and what lane does that correspond to on the device? That sort of information you can see, exactly where a problem is. And you can also say, hey, I want to look at a specific thread to see what that thread is doing. There are also some commands that control the behavior of the debugger. Again, to get a quick list of those, you can say set CUDA and then hit tab inside CUDA GDB, and tab complete will give you this list of things that you can do. A lot of these are pretty interesting. I'll just talk quickly about a few that I like. So this, in the first column there, break on launch is really helpful, and you can set that to just say every time I enter a CUDA kernel, set a breakpoint for me. You can set that to break either on application launches, meaning stuff you wrote, or system launches, which could be, maybe stuff coming from a library, or on both. So you can set it to all. So you can, that's pretty nice, just to be able to stop instead of going around and manually instrumenting all your kernels. The memcheck tool, that's pretty much exactly like the compute sanitizer version of memcheck, but you can also run that inside the debugger. Launch blocking is pretty useful. Like you might be having a bug that is some interaction in synchronization between your GPU code and your CPU code, and launch blocking will cause the kernels to block until they complete. Value extrapolation is one that's pretty helpful. Well, helpful, at least interesting, at least worth trying. So I mentioned earlier, sometimes there's some problems getting local state. Value extrapolation sort of helps the debugger guess what the value probably is. And I think, they say it's probably right, but it might not be exactly right. But it can be more helpful to have value extrapolated than have it simply not exist. And then I guess one more I'll mention quickly is that single stepping optimization. So running a CUDA code inside the debugger can be pretty slow if you're single stepping millions of threads. So these single stepping optimizations just speed things up, and they do it in a way that they pretty much guarantee is safe and will produce the same result. And again, any of these commands, if you want to know more detail on what they do from inside the debugger, you can type help command. So if I wanted to know about the break on launch, I could say help set CUDA break on launch, and it will tell me what that does. Real quick, I'll just go back through the using the memcheck tool. What if you had looked at that same problem from inside the debugger? To do that, I would start CUDA GDB on that bounds bug program. I would say set CUDA memcheck on and then run. And you can see again, it finds the problem straight away. One nice thing about being in the debugger is you get a little bit more information because the debugger has access to your source code. So again, I can see where the out of bounds write occurred here on line 10. And then I can also do a list and get some context for what's going on in the area around where the debugger paused. And again, it will print the exact thread that had the problem here. You can see there in the kernel call that it's identifying kernel 0, grid 1, block 1, thread 31. So, which is what we would expect. So again, you can run that tool outside of the debugger, and that's probably simpler, but you may want to run it inside the debugger as well while you're debugging a more complicated problem. Setting breakpoints. So again, this is just like setting a breakpoint on the CPU side, but they do also work inside kernels. They work very well inside CUDA kernels, a little less reliable inside OpenACC generated kernels. But again, looking at that, just using that bounds bug as a model here, set a breakpoint. There are many ways to do it. You can say break on a particular line. You can say break on a particular line within a particular file if you have a multi-file code. You can say break on the name of a kernel or the name of a function, or you can set that CUDA break on launch, and then it'll break every time it enters a kernel. So all those commands below in this case would be equivalent, doing all of those things. So breaking on line 9 or breaking on launch, all in this case, they would all stop the program at the same spot. So doing that here, if I wanted to say CUDA set break on launch, and then I say CUDA set break on launch application. Again, the application is saying break on kernels that I wrote. So then I tell it to run, and indeed you can see it stops in this kernel. It's stopping at line 9. It's stopping before we've hit the out of bounds access. So we would expect if we continued to run it from here, we would have a problem, but we would only catch that problem if we had the memcheck set. Now I can examine sort of exactly what thread is doing what. So when I set this breakpoint, the first thread to hit the breakpoint stopped the program. So if I say CUDA block thread, it will tell me what block and what thread I'm looking at right now. So CUDA block thread in this case says block 0, thread 0 is the one that hit the breakpoint first. So I can tell, you know what, going back real quick, I'm on line 9 here, which is saying X is about to get set to this variable. X is my index here. It's about to get set. So if I step the program once, now I will have gone through line 9, so X should be set now, and I'm paused on line 10. So now I should be able to print the value of X. Indeed, I can say P X, P is for print, and it says, okay, my index value for block 0, thread 0 is 0, just like we would expect. Now I can switch to the thread that I think is going to have a problem by saying CUDA block and thread and giving them arguments. So here I'm saying CUDA block 1, thread 31, switch my focus to that. You'll note that this goes back to line 9 because I only stepped the first thread. I haven't stepped this set yet, so it's still paused at the breakpoint on line 9. If I then go ahead and step this thread, it should have its index set. And now if I print the index of this thread, it says, oh, my index is 63. So again, just showing you how you can switch and examine the focus. This is all kind of like we would expect. Pretty useful to be able to look at different, you know, the different focuses and pay attention only to where you think a problem might be. This next slide is going to show, you know, some of the things you can do to examine the local state of a thread. This is using a kernel, the details of which don't matter particularly much, but I'm listing it here just to show you this is a kernel that has a lot of local state. So there's a lot of stuff we should be able to examine inside this kernel if we set a breakpoint in there and go through it. So here, I'm just setting a breakpoint inside this kernel. I'll go back real quick. I'm listing lines 66 through 94 of this kernel here where a lot of arithmetic occurs. So by the time I hit line 94, all of these things should be initialized and set to some value. So here I'm setting a breakpoint on line 94 and then telling the program to run to that point. So at the point I hit my breakpoint, I single stepped once to get the last value set. And so I've stepped to the closing bracket there. I've gone all the way through this kernel. And so now I can use, there's a variety of commands I could use to get local state. I can say info locals, that'll show me all my local variables. I could also do backtrace full. That will show me, you know, you give me a backtrace, and in addition, the full says, give me state information on my locals as well. And I can also print variables directly if there's a value of a particular variable I want. I can also do some math on variables. So I'll show a few of those things next. Here's a full backtrace after I've paused at that point. So you can see all these device variables do indeed have values, and they're accessible from within the debugger. And you know, I can print individual values, like here I'm saying, show me the values of V or offset, or I can do math with them. If I know, for instance, that these values should be the same, I can subtract them and try to verify if they're 0 or do ratios. So things like that. All the normal stuff you can do with variable values in CUDA, or sorry, on a CPU, you can also do with CUDA code. Then additionally, you can set watch points on these variables. So this can be helpful if you have a problem, for instance, like a numerical problem where a value is expected to be small but positive. Maybe at some point it goes negative. You can set a watch point. So you can see here, again, I'm running that same program. I'm breaking earlier at this point. I'm breaking sort of before all those values are computed, and I'm setting a watch point on, in this case, I just picked one at random, z1_imag. I'm saying set a watch point on that and notify me if it becomes negative. It sets a watch point. I then tell the program to continue. And indeed, at some point, it hits that watch point gets triggered. So it tells me the old value was 0, and now it's become -5. And it tells me that happened on line 68. And then it prints line 68 for me. And you'll notice that variable doesn't show up in line 68 on the left-hand side. It's being used on the right-hand side. So what's really happening here is the value changed on the previous line. So you would then, from this point, okay, well, its value changed around line 68. You probably want to do a list here to see the exact line it changed on. And in this case, its value was actually set on line 67. But these watch points work. I think one caveat on the device code, setting watch points on these variables, when you enter a kernel, a lot of these variables won't have values yet. And the way GDB will see them is it'll say that the value has been optimized out. And it will not let you set a watch point on a variable that whose value it believes has been optimized out. So what will happen is every time a new thread block hits a kernel, it will remove a watch point for you because it says, oh, I can't watch a variable that doesn't have a value. So you're going to end up having to set breakpoints and watch points a lot, unfortunately, because they get automatically cleared by GDB. But they can still be pretty useful, but just expect you might have to repeatedly set them. Okay, and here's a problem that I encountered somewhat frequently in putting this talk together with trying to use CUDA GDB on OpenACC code. This seemed to be particularly problematic with Fortran OpenACC. This is a matrix multiplication example. Here I'm just trying to run it in the debugger, and it causes the debugger itself to segfault. That's something I hit a few times. So, just to point out here that the debuggers aren't perfect, and you might hit problems like this. So it's good to have a backup plan. I wouldn't say CUDA GDB should be your only plan for debugging your code. And that's why I want to talk real briefly, because I probably got about 12 minutes here. I want to talk pretty briefly about an alternative, which is DDT from ARM. It's a little more heavyweight to set up versus CUDA GDB. It's got a graphical user interface as sort of the primary way you work with the tool. That's either a benefit, like a feature, or a drawback, depending on your point of view. I like their interface. I think it's pretty good. As far as GUI tools in HPC go, I really can't get much better. It's pretty responsive because the client runs locally on your machine and connects via SSH to where the debugging is going on. We have a lot of documentation on setting it up, so I won't really cover that here, but you can look in our knowledge base articles on getting DDT set up. So quickly, in order to start it, the way I find it most convenient to start is this reverse connect method. So here I am on a node where I'm going to be doing some debugging, and I can say forge -- connect, and then my program. So like in this case, that matrix multiplication example. You can also, forge again is sort of DDT or map. It's the combined tool. I could also say map -- connect or DDT -- connect. In this case, I would say DDT -- connect to launch the debugger. But any three of those invocations will bring you to this screen. And then, so I've told my local client to connect to Casper and listen for connections. It finds one. All I have to do is click accept. After I accept the connection, I'll get a screen where it will give me some options I can set. You'll see here over on the left-hand side, those blue checkboxes. I've selected the CUDA debugging options, and selecting CUDA debugging also turns on memory debugging for me. And then after I click run, it will start my program. It opens up my source code listing, and the program is in a paused state. So I would then, in the upper left, hit that green arrow if I wanted to start running through the program. I could also at this point set breakpoints. So looking here over on the left-hand side, you'll see a red dot on line 98. That's all I've done is I've clicked the cursor on line 98. That's all you have to do to set a breakpoint. So that red dot means I've set a breakpoint there. I've run the program and had it stop at that breakpoint. And you'll see all these blue lines running horizontally through the source code. Those blue lines are locations where various CUDA threads are paused. So all of the threads in this program are paused on one of those lines. If you go to this top part of the screen where I've got an oval circled, that's where your focus is. So it's showing me here. I know this is a bit of an eye chart in slide form, but it's telling me I'm currently looking on block 1, thread 37. it tells me some information about my overall grid, which here is 65, 535 by 1 by 1 with 128 threads in a block. And then again, I can click up or down or type in those boxes if I want to examine the state of a different thread. And then over on the right-hand side, the oval I've got circled there, that's the local state information for this particular thread. So it's got its portion of the A and B arrays and its portion of the output array. It knows its block dimensions and block index. So I'm really just showing here that this is that same code that caused CUDA-GDB to dump core. ARM is able to debug this OpenACC code without any trouble. So I do think if you're having an OpenACC bug, I would probably turn to this tool first. And I think it's a good thing to be familiar with generally. I think the explorability of the code inside the GUI to me is a little bit better. This is just another slide debugging now that memory problem. So again, showing that ARM would stop and catch like an out of bounds write in a similar way. So here I've just loaded that program and run it, and I don't even need to set a breakpoint or anything. It automatically will break when it notices this out of bounds access and pauses execution on the line. You can see the line highlighted up here. That's the out of bounds write. So it caught that without any trouble. Okay, so quickly a debrief on debugging. I guess what's my overall view? If you're familiar with one of these two tools already, then I'd go ahead and say start with the tool you're familiar with. If you're not familiar with either one, if you have a Fortran OpenACC code, I'd probably skip CUDA-GDB, at least for now. ARM DDT tends to do better with that. If you have a CUDA code, I think CUDA-GDB is a great tool. So I would definitely endorse it for doing debugging of CUDA code. But again, in the particular case of debugging GPU stuff, I think there's a lot of stuff you can do before even getting a debugger out that's worth your time. So things like checking error return codes, that's a great idea. Putting those CUDA checks around all your CUDA calls is really helpful. Those debug environment variables can be helpful. The compute sanitizer tool is really great for catching, a pretty common class of bugs like memory issues. And then, becoming okay with using printf. I think printf on the GPU can actually be a pretty efficient tool if it's used judiciously. And then again, for OpenACC, one other thing you can do if you have a problem in an OpenACC kernel, but the problem is a software problem that's not really related to the GPU, you can always target the CPU instead of the GPU and then debug the OpenACC on the CPU. So that's another approach you can explore if you have an OpenACC problem. I'm going to cover profiling real briefly in my 6 remaining minutes here. I just want to say that both of these tools, both the NVIDIA toolchain and the ARM toolchain, do have profilers. In a future workshop session, Daniel's going to talk a lot more about NVIDIA's Insight tool, and particularly the GUI version. So I'm just going to briefly mention the CLI version of that tool here. The CLI version is a pretty useful tool. And then I'll talk a little bit about map. So this is just the CLI version for NVIDIA's profiler tool. It's got a plethora of sub options. So, -- help on NV Insight CU CLI is sort of the command line interface. -- help will give you all the gory details of what you can do. I'm showing below a really basic usage of it, and that's just saying run the profiler, profile 100 launches of my kernel, skip the first one, and then giving it my code. This MW_OpenACC is the mini weather app we've talked about before. So I launched the profiler on it. It gives me a lot of profiling output. You can see I've told it to go 100 times, so it's just telling me, okay, I've done 1 of 100, 2 of 100, 3 of 100, et cetera, until it gets to 100 of 100. It'll stop profiling. And then it will produce a report for me. So the reports are pretty nice, I think. They're pretty verbose, but in a nice way. They're not overwhelmingly verbose. They're summarized pretty nicely. So they've got different sections. This is what they call the speed of light throughput section. This very top line here is Z28 compute tendencies, et cetera, et cetera. That's a CUDA kernel that's got a mangled name that came from the OpenACC inside the mini weather app. So that's the name of the kernel it's talking about in this report. It'll produce one of these reports for each of the kernels in a code. I'm just looking at that one now though. And it's giving me some useful statistics here about RAM, about so global memory, about the shared memory on the device, just basic throughput numbers, and then cache, all the whole memory hierarchy here. And then at the bottom, it gives a little text description of what it thinks is happening in this kernel. So it's saying it has low compute throughput and low bandwidth utilization relative to the peak. And so it's giving you some guidance. It's saying, this could be a problem. You might want to go look at compute throughput in more detail. Another of the reports it produces for the same kernel is launch statistics. So here it's showing you, kind of how you're launching this and how it's being called. And in the little text report at the bottom here, it'll say, in particular, it's saying like it has, right. So it's not satisfied. It's only using 3 full waves and 1 partial wave of 100 thread blocks. So it's telling you it thinks you should launch a grid in a different way, maybe to try to get better occupancy. So again, it's kind of a nice bit of feedback in the sense that it's pretty specific and it's telling you a thing to try. Whether or not that thing pans out, hard to say. And again, here's a section on occupancy. So again, it's saying here, theoretical occupancy should be 62.5. It's limited by the number of registers, blah, blah, blah. So it's kind of a nice read of saying, I looked at your code. Here's what I think could be a problem. Here's something I think you could try to maybe make your code work a little bit better. So even in really basic form, how I've launched that tool, I think it can be pretty useful to run in your code. It's very sort of low-hanging fruit. It's really easy to use. So getting those profiles listed out and having it give you a little advice, I think it's a pretty good idea because it's very effortless to produce those reports at least. Quickly, I'll just in a couple minutes here show doing the same thing with maps. So launching this is done in the same way as launching DDT, doing map -- connect from, this would be like from a Casper compute node that I'd be doing this. And then again, on the mini weather app, this brings up like a configuration screen where I've checked some boxes telling it the type of things I want it to profile. So here I'm asking it, in particular, that last box I've checked, I'm saying, please profile NVIDIA stuff for me. Then I click run, and it will bring up a graphical view of my code. In these little red ovals, I've circled some of the important information. If you look at the lowest one, that's like the most expensive single routine. So that's a thing called semi-discrete step. Then if you look in the code, this top circle I've covered, I'm highlighting the particular line that it's referring to that's the most expensive call. And then I can, within that line, I can click on that. I could right click on semi-discrete step and say, take me to that within the source code. It just so happens that in this source code, that semi-discrete step is directly below. So you can actually see the start of that subroutine here. The middle oval there, where you can see the 57.9%. So that's where most of the time is being spent inside this most expensive kernel. Again, I can navigate around on these things just by clicking. So I can see the most expensive thing occurring there is this set halo values, and that is a kernel. So I can go to that set halo values and I can see what's going on. And here is sort of an expensive part that is actually an OpenACC loop. So this is the first, you can see the line above, that's an expensive portion that's doing a lot of MPI traffic, but this particular 10% at least right here is coming from this ACC parallel loop. So this might be a place where you want to examine your loop and say, should I be spending 10% of my time here? What's going on in this loop? Can I improve it? Quickly, I'll show a couple things you can do on this top bar too. So if you look at this lower right red circle I've got over there, these zoom controls, and in there I've selected, there's a drop down. I clicked on it and said, show me information about GPU utilization. This top bar, which is very colorful from left to right, is basically a timeline of the execution of your code, with purple corresponding to accelerator activity and blue corresponding to MPI and green corresponding to CPU compute and the sort of orange corresponding to IO. So that's kind of the major thing happening as time goes on in your kernel. And then you can sort of scroll through that and see statistics change at different points in your kernel. There are other things you can look at. So here's another drop down where I asked it to show me host to device memory transfer, device to host memory transfer, and then off device memory transfer. And you can see that vary at different points in the kernel. And then you can, as you are sort of sliding the cursor around, you can correlate those points of activity with lines of source code. So I think it's a nice exploration tool. I think both these tools are worth using to just get a better picture of the performance of your code. Again, I mean, that was a very shallow discussion of these. So if you want more help with either of these tools, feel free to reach out to us at CSG and we can help you get set up running these tools. And I think in the future, we're likely to have vendor provided trainings, at least from ARM. We haven't had one of those for a while, but we used to have them come in and give talks. So if we have a vendor provided training on any of these tools, that will be announced widely within the lab, but it'll certainly make its way to people that are in this workshop too. So I can take questions if there are any now, or maybe wait until Daniel's done with his presentation. And if we don't get to questions that you have today, feel free to contact me offline and I'd be happy to help. Thanks a lot.
Any questions right now, or do we transition to my portion of the slides?
Yeah, maybe I'll ask a quick question to start things off. I guess Rory or Daniel, do you know what the advertised capability of these tools is for like OpenMP offload?
I don't know for OpenMP specifically, like versus OpenACC specifically, you mean?
Yeah.
No, I don't know. I suspect it would be similar, would be my guess, because at the end of the day, at least on an NVIDIA hardware, they're both, generating CUDA behind the scenes in some way. So I would expect the OpenMP offload capabilities to be similar for both tools to the OpenACC, meaning I would expect that MAP probably handles OpenMP offload better than CUDA GDB does, but I didn't actually test an OpenMP code specifically here, so that's kind of speculation.
Thanks, makes sense.
Any other questions? Don't see any in the chat, so I think I might just go ahead and press on with my section. So I'll be talking about another tool in the space of various tools you can use for GPU development. I'll be focusing on the usage of integrated development environments. You might know them as IDEs. There are many options for that, but specifically I'm going to focus on the Eclipse Parallel Tools platform and its integration with the some Nsight plugins, as NVIDIA calls them, towards enabling certain GPU-specific debugging, profiling, or analysis of code from within that IDE environment. So why use an integrated development IDE in the first place? Essentially, there's just many features across these types of tools that help you go beyond what a typical kind of a text editor you might have for managing and working with your code and software project, because you might not need it helps integrate the whole system of like various different code files might be working with, such that they're much more easily navigable, and you can there's an automatically managed build process that can be integrated in IDEs. For many nowadays, you can remotely run and synchronize code between, say, your local machine and then Casper or Cheyenne, for example, or other HPC clusters. There's syntax highlighting and auto-completion that's more robust typically than the highlighting that's available, say, like in Vim. And it can be augmented like it has been with Fortran and C codes to even like recognize specifically, OpenACC directives. So you see in this screenshot here, our comments, even though like, OpenACC directives are comments, they are highlighted differently than just a normal comment. And that is due to how this IDE is able to process through the various plugins that it's installed to recognize the sort of distinctions. You can do the same with CUDA code or any other CUDA code through that integration with Nsight and other language features that are now a standard in IDEs. So through these the same, there's also opportunities for more robust and intuitive debugging. Whether or not that's better than ARM DDT or the command line interface of CUDA GDB, that's for you to determine. And in some cases, it is in fact a little bit difficult to set up a debugger through the IDE, especially on a remote cluster. I don't necessarily even have time, I believe, today to go into that process with Eclipse, for setting up the CUDA GDB here, but it would function the same where you can highlight each line and say set a breakpoint, and it would look just like how you saw earlier with ARM DDT. So lastly, you have this sort of like, arrangement of windows and other sort of different ways you can customize your window that you're interacting with your code and project you might be working on, such that it's easier to say like navigate around source files. You can even navigate within source files, and the IDE will analyze, say, which functions or subroutines are within that source file. And you can click them, see on the right pane, and it'll just allow you to jump right back and forth between functions. And it's a easier experience, I think, in terms of just like getting you a more clear interface with your code. That's especially more useful as your software projects become much more complex and more difficult to navigate with many multiple source files or other just complex interactions between different parts of your source code. So again, this is also customizable and has many other features you can explore. There's lots of extensions or plugins that are available in things like Eclipse, but I'll go through some of them in the next few slides. So just to go over, just kind of like getting it set up, you can download Eclipse at eclipse.org/downloads. It will require the Java development kit in order for, that's because Eclipse is written in Java essentially. So if you have like a Mac, you might be required to navigate that process, though the installer itself does include a process to install it for you. I suggest using that Parallel Tools platform, as that is specifically meant for scientific development. So be sure that basically if you go download the Eclipse installer, it'll give you an option to select different flavors of Eclipse, and I would suggest looking for the Eclipse IDE for scientific computing, which is essentially this PTP platform. Additionally, for then integrating with some of the CUDA and GPU issues options available through at least in NVIDIA GPU debugging or syntax hiding and other features, you need to install the CUDA toolkit. No local GPU is necessarily required for this. Nonetheless, it does help in terms of say syntax highlighting and linking up with say if you are calling an external CUDA function, it can say find the information about that more easily in terms of if you had like if you wanted to highlight a function within your IDE, and then you can say, tell me more information about it. There's like a help option, and thus then you can get the function prototype for say that CUDA call if you have that linked appropriately with your IDE. For Mac users, that CUDA toolkit is incomplete, so there's not really anything to install, but there will still be a specific plugins that can still be useful for having partial support of Insight development of GPU code on a local Mac machine. That is located within an Insight EE_plugins folder in the installation location of the CUDA toolkit. Or if you have access to these slides, you can just download directly that zip file that is inside that folder, both on Glade or wherever you might be installing your CUDA toolkit. So you just want to notate where that is. But nonetheless, I'm focusing on Eclipse today. There are alternate IDE options, and use whatever is most familiar to you. I'd recommend that primarily if you have a preferred tool. It doesn't necessarily have to be Eclipse. It could be Visual Studio. It could be NetBeans. It could be there's many options out there nowadays. Xcode is technically an IDE. Just some of them have more support currently for integrating with GPU development. So I'm highlighting these two options here that have increased amount of support and community around making GPU development easier with these particular IDEs. If you do have an interest more into Visual Studio Code as your IDE of choice, feel free to explore that. There are some GTC talks on that particular IDE. So for integrating Insight Eclipse Edition plugins into your Eclipse installation, essentially you would go into the Eclipse. Once you install it and everything, you open it up. You can then select help from the menu bar, and then select install new software. You then add new software, essentially, was what we're doing, and then you select name the software you're adding. Here I'm just naming it Insight EE for Eclipse Edition. And then you're going to find that archive we had earlier of those plugins that NVIDIA releases with its CUDA toolkit. You click add, and you want to then select all the CUDA main features, basically the different plugin features that will then be integrated with your Eclipse installation, and then click finish. And this basically builds out support and offers additional selections within the Eclipse IDE for, say, debugging C++ code, C++ code primarily, but also Fortran code, and interfacing those that workflow with some of the cool tools discussed previously, like CUDA GDB, and other aspects of GPU development. Again, as before, it tends to be more useful for CUDA code, but there is still some utility for OpenACC. So I appreciate that highlighting from earlier that ARM DDT, which you do have access to, which is licensed on the Casper cluster, that tends to perform better with OpenACC. So if you do have a good CUDA code, it might be useful to use Eclipse here in this kind of interface. Otherwise, OpenACC code might be better for, say, debugging specifically on ARM DDT. Nonetheless, this tool at least allows you the ability to locally edit and manage and develop your code, and also then integrate it with building and deploying on the cluster in a seamless kind of one-click button manner. So next few slides are going to show that kind of process of integrating Eclipse with Casper, only, but it could be applied to Cheyenne as well. So to add basically to connect to Casper, you basically have to add first that remote connection and let Eclipse know that connection is something you want to use. So if you say are starting a new code project or new software project, you'd say you could use the new synchronized project wizard, or you could just go to the in the preferences option, which is in Mac, it's in Eclipse main menu, or it's in the window menu in Windows or Linux. You then select remote development and remote connections. You then input your host name, which is in this case for Casper, casper.ucar.edu. You want to put your username and then say password-based authentication. You leave that field blank because we actually don't pass a password initially when you SSH to Casper. You then get that token response prompt with Duo. So you have to navigate that process without through the 2FA by leaving that password field blank. Unfortunately, there's not really a way to make that automated without direct interaction, and that's just for cybersecurity reasons why that option is not available to make this happen without, say, user intervention each time you open up Eclipse. Once you have the remote connection added, you can then say add a remote development project to Eclipse. So you can basically you'll be using a synchronized project that might have been with that synchronized project wizard I just mentioned earlier. And then that can work alongside Git essentially to sync files between local and remote on-glade. So typically you'll be wanting to do this within a Git project that helps manage that sharing of files between your local machine and the remote machine. As you're updating files, it's not necessarily making new commits to the GitHub repo each time, but you can integrate your IDE with Git to do that as well through distinct processes. But I won't be covering Git specifically in Eclipse today. So to add that remote development project, you want to say select a new project. You can then say right-click in this Project Explorer pane here in the middle here. You can click New and then click Project, or this button up here for New Project. Once you click New Project, you'll get this sort of wizard window. And right here, you want to go to say the language or the type of project you're working on, and there'll be an option for a synchronized version of that project. You want to click that, and after you set up that, select that synchronized project, another window will come up, and you'll be able to name that project however you like. You'll have a local location you can specify where it's at, and this will be in the workspace that Eclipse will create when you first initialize it. But more importantly will be the remote connection and where that directory you'll be syncing with on Casper in this case. So you want to set your connection name to Casper, and then you want to set the remote directories. You want to keep synchronized files between your local and the Casper Glade file system to the location where you want to do that. So if If that folder does not exist yet, it'll create a new folder. If that folder already exists, that's fine as well. You want to, if you do an already existing folder, you want to make sure you select an empty project. Otherwise, you can always do these kind of like, bare bones kind of already template projects if you want to like build off something from scratch, but like not entirely from scratch. But nonetheless, once you select that GPU workshop, then you'll have then that new project that'll come up here. It'll be empty initially. So what you want to do to then say pull down files from Casper into your local machine, you then want to right click it, go to synchronize, and then sync active now. And that will then synchronize your files back and forth between your local machine and the Casper machine. So then moving forward, if you go back and forth with the editing pane, each time you save, you'll automatically see a progress bar in the bottom left or progress pane, and additional steps being done in the background, syncing those files actively each time you make a change. So that's one way to navigate that more intuitively, rather than say, editing a file somewhere and making sure that one is updated to another and making sure you're doing git push pulls appropriately. Basically, this is helping, the IDE is helping you do that all for you automatically, so it's less to worry about. During that process, you can then set up remote builds on Casper from Eclipse. You can say, you can go to that project you just made, you can right click it and select properties, go to synchronize. I can then use an environment management system. So then, the Eclipse is smart enough to know, what modules are available on Casper. You can select which ones you want to have loaded during the build process, and manage that appropriately. And after you have that set up, you can then go to the Fortran build process and like make a build configuration. This can be, say, through a make command or a specific compiler command, depending on the type of build process you want to be using. And all this is very configurable towards what you need. And once you have it all set up, it's just a single button to say build your new code, and compile it and go through the whole sequence. And it's not necessarily doing it in your local machine, it's actually pushing that build onto Casper for you with that environment you specified earlier. So having this all in place is very helpful towards once you have it set up. Once you have, say, a build process set up, you can set up remote runs on Casper from Eclipse. There's a green arrow icon you might see, and that's basically to run your program after it's built. You can set up to build a parallel application, for example. Interfacing with the PBS batch system in Casper is not intuitive in the sense of like the generic templates that are provided with Eclipse. So in this case, it's typically recommended to select the import PBS script tab in order to specify exactly how you want to be running jobs and submitting to the batch system. From there, this is just due to the heterogeneous nature of Casper specifically, that the options don't quite work out of the box from the template files that you might see in the other tabs there. It is possible to make your own template, but that might be, depending on your interest, just in time available, that might not be as useful. But from there, essentially, this just allows you, again, automating that process of setting a build up, and then each time you maybe save your files, it automatically build, and then each time you then want to run and test your code, you can just click one button and it'll submit a batch job, and you can then see the results interactively, and the IDE will report when your job is accepted and processed. So there are additional features with Eclipse PTP, or Eclipse in general. Doesn't have to be within PTP as well. If you're a C++ developer and you don't want the PTP platform, you can do the CDT flavor. But nonetheless, there's a whole marketplace of add-ons. One favorite I have is Code Together. This one enables paired and group programming. There's free versions available that that limits, say, the amount of concurrent users that you can share a Code Together link with. And then there's a paid version that allows a larger amount, but nonetheless, the free one is actually pretty accessible towards, say, small software development teams, and that could be very helpful towards collaborating with your colleagues on development process. And basically, they don't necessarily need to have Eclipse installed to use it. They can do it within a web browser for a link you provide them. But nonetheless, this just provides a way to enable collaboration in a seamless way through an IDE, rather than trying to do that back and forth of Git and asynchronous kind of mode of development. Another useful tool to mention, essentially for this Code Together, just before I move on, once you have it installed, you can say, like, right click in your editor, you can say start hosting session, and that'll be give you the process to initiate that code together paired programming, for example. Another tool to just like important feature to emphasize, especially in Fortran, because it's not automatically enabled by default, is refactoring and analysis tools. So essentially, if you go to the properties for your project, you can then go to like Fortran in general and analysis refactoring kind of tab, and then you can enable these options here. And this basically enables a lot of like context aware in terms of assistance, in terms of like as you're developing your code, such as you highlight a function you're calling, you don't quite remember the prototype of that function and what variables go into it, and the IDE will tell you just by hovering over it or using control space, it can autocomplete things. It can show you exactly what's supposed to go where, and just help speed up the process in terms of navigating, say, larger and larger code projects that might have many functions that are very difficult to keep in your head at all times, and the IDE can do that for you to assist that development. So in summary, there's a very extensive guide for using Eclipse in terms of parallel development and scientific computing development. So I encourage you to review that documentation there. There's a more long form talk already given on scientific software development with Eclipse as part of the IDEs productivity project and given by Greg Watson at Oak Ridge National Lab. But Eclipse and other IDEs in general, they provide a variety of features for software development, GPU development included. I can share some specific ways to integrate Eclipse with CUDA GDB, for example. It's just not enough time to discuss that. But I emphasize the Eclipse PTE mainly because it caters to scientific and HPC software development. So you're allowed to do whatever you want, what's most comfortable to you in terms of just if you want to stick with the text editor or whatever workflow you have towards managing your software. But the argument, at least here, is still that IDEs give an automated and managed control during development. So you have a lot more flexibility and ability to optimize how you're developing your software through an IDE. And as you get larger, more complex workflows, and IDEs can very much so manage that complexity for you in a much more seamless manner. Nonetheless, as I've gone through these slides, it does require some extra work to configure that IDE for these benefits. And hopefully, as you might explore and download it and play around with it yourself, you can explore these in your own time. And feel free to reach out to me or anyone else on the GPU workshop team for maybe best practices of navigating that development process. But that's all I have for discussing Eclipse. Thank you for your time. If there's any questions, feel free to add it in the chat, and happy to have you here today. I'm going to go ahead and pause the stop the recording.